Hello everyone. The fourth and final application of differentiation is rate of change. Now the most important thing regarding rate of change is actually the chain rule. In the differential form, the chain rule can be written as dy over dt equals to dy over dx times dx over dt. Obviously, this y, t, and x can all be changed for something different. Now if you look over here, we see that we can kind of like treat the differentials as somewhat like fractions, although I can tell you that they are definitely not fractions. That's just the magic of this notation. Now let's try a question. Water is transferred at a rate of 64 pi cm cubed per second to an empty inverted right cone with a base radius 8 cm and height 16 cm. Given that v cm cubed is the amount of water in the cone at any time t seconds, find v in terms of the height of the water h. First, the question guides us to do this. From mensuration, we know that v equals to 1/3 pi r square h, where r is the base radius and h is the height of the cone. So if you look over here, this is kind of like a similar triangles with r and h. We can tell that h is always going to be 2 times of r. If we do the relationship in terms of similar triangles, we should get h over 16 equals to r over 8. But visually, you can also see that h will be always 2 times that of r, no matter where you are. And knowing this fact, we can take 1/3 pi and replace r with h over 2. So we get h over 2 square and then times h. And if we simplify that, we get 1 over 12 pi h cubed. So we have found v in terms of the height of water h. Now what I want you to take away from this is that for rate of change, when there are two variables over here, two unknown variables, we usually like to express one variable in terms of another variable in order to eliminate one of the unknowns. We'll see how this is useful in part B, where we want to find the rate of change of the height of the water level when h equals to 6 cm. So by using the chain rule up here, we can say that dv over dt equals to dv over dh times dh over dt. Again, you can kind of like treat them like fractions where we can cancel this out, but I need you to remember that they are not fractions. We can just treat it like that because of the magic of this notation. Now dv over dt will be the rate of transfer of water, or the rate of change of the volume of water. dv over dh will be the rate of change of the volume in terms of the height. And finally, dh over dt is the rate of change of the height of the water level. So if you want to find dh over dt when h equals to 6, this will be equal to dv over dt divided by dv over dh when h equals to 6. What we know is dv over dt is 64 pi. And over here, let's just find dv over dh. dv over dh will be 1/4 pi h squared. You are differentiating v in terms of h. So here, you should get 1/4 pi, and in this case, h is just 6 squared. And this should get us 64 over 9, and let's give units, cm per second. Now again, I want you to digest what we're doing over here. The first step is to express one variable in terms of another so that you can find the volume in terms of just one variable, in this case h. We're using the information of the base radius and the height in order to use similar triangles to find out this relation. And finally, to answer the question on the rate of change of the height of the water level, what we want to do is to find the connected rate of change, and you can remember this by seeing that the dx's or the dh's over here kind of cancel out, although again, they are not fractions. And after we have this connected rate, we can then find out what dh over dt is. Once you practice more rate of change questions, the whole process becomes more and more clear to you. Thank you so much for watching. I hope you have learned more about rate of change.